the first step is to download and install ChimeraX. This link will take you to the download page, or you can simply Google ChimeraX download. And once you've installed it, we can open it. Here I have two different versions, 1.8, 1.9. Let me start 1.9. Now we will use two plugins in this exercise, and they can be installed with more tools, which brings up the ChimeraX toolshed. And first I will search for Q-score. Oh, this is the search box here. And Q-score. And if it's not installed already, you will see an install button. And once you press it, it will be installed. Next, I will search for Clipper. The same button will appear. And then also for ISOLDE. Okay, once these are installed, we will obtain a map, a cryo-EM map, and we will use the map in the EMDB, which is the electron microscopy database. This is one of the portals for the EMDB. Make a search for different maps and models. And for a record such as this one, there's a download tab, so you can download it from here. Or more simply in ChimeraX, we can just run the command open, then the map ID, and from EMDB. So if I go to ChimeraX and copy this command, it will open the map. Now it loads up really quick here because I had downloaded it before and it's cached in the downloads folder. By default, you will see a step of two. This is to save memory, but for the most detail, we change it to step of one. And you'll notice in ChimeraX, you have these floatable dialogues and you can redock them. I like to put them on top of each other and then they can be accessed with the tabs at the bottom. Okay, in ChimeraX, the left mouse button rotates the map and we can set, for example, right mouse mode to translate or to zoom. With a mouse, you can zoom with the wheel as well. And I have a 3-button mouse, so I have the middle mouse button to pan. Okay, next thing we will do is we will generate an AlphaFold model. This is the sequence of the protein. So we will bring up AlphaFold with tools, structure prediction AlphaFold. And with AlphaFold, we can try to do a fetch. And if the sequence already has a predicted model in the AlphaFold DB, fetch will open it. Search will search for similar sequences, and predict will do a full prediction, which can take a little bit longer. So fetch is faster for in this case. Okay, the AlphaFold model is open in an arbitrary position here. And now the next step is to try to fit this model into the map. So you'll notice this map is larger than the model, and because of it has symmetry, it has multiple copies of the same protein. Now it's hard to see each individual protein in this complex because there's a lot of detail, so it's hard to see the boundaries. So one trick that I use is to use tools, volume data, map filter, and what we will do is we will apply a Gaussian filter of width 2 to this map. And this will lower the amount of detail in the map. It will basically bring it down to a lower resolution. And in this case, close to like a 10 angstrom resolution, I would say. And here we can see secondary structures of helices and loop-like densities. So now I will try to match the model secondary structures to the map secondary structures to find the correct position of the protein. And I can use the right mouse mode, move model. And for this to work, the model has to be selected. So you can select it by control, click, drag around it. Or in the models panel, I can click on the selection checkbox here. Now, if I use the right mouse mode, it will move the model independently of the map. The left mouse button still rotates all of them together. The mouse wheel also does that, and the panning, you might have to switch back and forth between panning, moving, and rotating. So let me try to align uh, the secondary structures here. And let's say I have an initial alignment like this, then I can use tools, volume data, fit and map to refine this fit. So I select the model, it's already selected, and I want to fit to the Gaussian map first because it has less detail. And the model will be less likely to get stuck in a local minimum. So I press fit, and in this case, it doesn't look that great. So let me try to change the orientation a little bit. So this might take some trial and error. This doesn't look that great either. Okay, okay, that looks interesting. Now I see like this helix here is still not fitting properly. And one thing to help actually is to change the color of the map. So let me change it to a gray and make it transparent. So I can see, yeah, that the secondary structures don't really match that well. Let me try to rotate it the other way, something like this. And just move it a little bit here. Fit and map, fit. Okay, that looks pretty good. All the secondary structures are matching here. Now switch to the original map and do one more time the fit. It will move just a little bit because it's now using the original map with more detail. So back in models or volume viewer, I can close the Gaussian map and this icon will show the original map. Let's look at the density around just the model. So to do that, we can use the volume zone command. Zones the volume, and this is the ID of the map that I want to zone. Near atoms, cell means whatever is selected, and range 2. So anything within 2 angstroms of the atoms in the model will be shown. So let's try this. Okay, so I can see just the density around the model. Let's make this one transparent as well. Oh, under graphics, there are some useful buttons here. You can make the background black or white, change to a soft shading model or simple. The molecule display, let me show the side chains here. So the side chains are now appearing. And to make them have colors that correspond to atom types, I can do actions, color by element. So now carbons are shown as gray, nitrogen says blue, oxygen says red. And here I have my middle mouse button, you'll notice is focusing on a particular point or sets the pivot. So this is something useful for navigating. If you don't have a middle mouse button, you can do right mouse mode pivot, and this will do the same thing. So it will change the pivot point to something that you click on, and that can be very useful for navigating. Okay, now in the volume viewer, I can use the bar to change the contour level of the map. And one thing that's interesting that you'll notice is that the model fits mostly okay, but the side chains might not fit too well. So for example, this phenylalanine is a little bit outside of the density. And that's because the Alphafold method doesn't look at this map in particular. So the conformation might not match exactly our experimental map here. Notice this arginine as well is also outside of the density. Another way to visualize how well the model fits in the map is to use the Q-score plugin, which we already installed. So I can open it from Tools, Validation, Model Map Q-score, and it will open up this dialog. So here I can select the model and the map, and I can press Calculate. And this will show for every residue. Every residue has an ID from 0 to all the way to 180 or so. And this is each point represents the Q-score of a residue. So the higher the Q-score, the better the fit to the map is, and the better the map is resolved. So for example, this residue is quite well resolved. If I click on a low Q-score, I can see that the model does not fit to the map very well, or in some cases it could be that the map is just not resolved in that area. So some side chains are more flexible, or they could be damaged by radiation, and the density is just not there. It's blurred out or blurry. So if I go back to here, I can try to fit this residue or the model better into the map, and for that we will use ISOLDE. To start ISOLDE, first I have to use Clipper to associate. So Clipper, associate, or SOC for short. And then I have to say the map, which is model ID 1, model ID 1, to the model, which is model ID 2. And now the display will change slightly with ISOLDE. So you'll notice the map, it's changed a little bit, and that's just to make it easier to visualize some of the inner parts of a protein. Another thing I need for ISOLDE is, because it's based on molecular dynamics, I have to add hydrogens because that's required for molecular dynamics. And once that's done, I can either type ISOLDE start, or I can go to the ISOLDE tab here and then say start ISOLDE. And what this will do is it will actually select the entire model by default. So when I press start simulation, whatever is selected will actually start moving and move into the density. So I do start simulation, you'll notice how now the residue moves into the density. So the fit to map is overall better now, or should be. And I can check that by going back to model map Q-score, uh, and then selecting the model again. Because Clipper changed the model IDs, I have to reselect them in here, press calculate. And now you'll notice, or if you remember, more of the points have higher Q-scores because they moved more into the density. And I can check if there's any residues that could use a bit of tweaking. So for example, here I can see that there's a bit of density for this residue, but ISOLDE doesn't, or molecular dynamics doesn't actually move it into there because it's just a little bit too far away. So I can nudge it into the density with the right mouse button on an atom, and then I can drag it, and that will move it into the density in this case. This one is not resolved, so there's not much to be done, but you can keep looking for residues. Okay, this one's kind of interesting because it looks like it has density, but again, the model is a bit too far to move into the density. A little bit of nudging. And this is part of modeling. You'll notice, you will see that there is many cases in which you need to interactively guide it. So here that looks a little bit better. And you notice in this case, it's interesting because it has two bumps here, but it also looks like it could fit potentially this way. So this is an example of potentially an alternate conformation. So, and because the map is an average of many particles, and some particles, the side chain might be in one conformation, and then another, and some other particles that could be in another conformation. So this looks kind of okay here. And whenever you stop it, you can recalculate. Here's another case where it could use a little bit of manual intervention. Yeah, that looks a lot better. Calculate here again. Yeah, you notice that went way up. And in this case, this just doesn't look. It's the basics of cryo-EM modeling. We did rigid fitting, then we calculated Q-scores, and then we used ISOLDE to fit better into the map.